Okay, spring break next week, unfortunately. So we are done with the unit about potential. And again, at the end of the book, at the end of the chapter, there is no attendance today. You have a very nice summary here. So don't confuse the electrostatic energy with the voltage or the electric potential or the potential difference. So a voltage is at a given point. Okay, it's a scalar at a given point. So that will be the energy, okay, of 1 coulomb of charge placed at that point P. Okay, in that neighborhood here. So that means how much work you have to do to bring that charge over there. If the work is positive, that means the potential energy is positive. That means it's not happy to be there. It wants to go down the potential if it's positive, okay, because it's 1 coulomb of charge. If the potential is negative, so then it's happy, it's binding, and you will have, you did negative work, meaning you have to refrain that charge to go there. Okay, so that's for the voltage. And the voltage is a property of 2 points. So when you are finding the voltage at point P, that will be the energy for 1 coulomb of charge placed at that point relative to the ground or relative to infinity. But infinity doesn't exist in reality, so it's just relative to far away. Now, if you talk about the electrostatic energy, so that will be the potential energy. So that will be the energy of a configuration. Okay, so you place a charge here. So then how much energy this configuration will have, and you do not have the same equation. Okay, so that will be in volt and that will be in joule. So in the water molecule, you're going to have potential energy. Okay, we did that computation last time. Okay, so it's a very nice summary. So you can go over that. We talked about equipotential. So for the test, remember the electric field is always perpendicular to the equipotential, and it's showing which direction to go for a positive charge to go down the potential. So the electric field is like a restoring force. It wants to lower the potential energy. So if it's a positive charge, it wants to go along the electric field. Negative charge wants to go against the electric field. And then we did a little bit of calculus, like it's called vector calculus. So the electric field is the gradient of the voltage, or the electric field is the slope. So in 1D, it's easy, it's just the slope. But in 3D, yeah, at one point you can have many slopes, right? So the electric field will be the largest slope, the steepest slope. And to do that, you have to take the gradient, because you have to go from a scalar, which is a voltage, to a vector, which is electric field. And you have this equation, which is fine. It's calculus, but it's not that hard. And then, okay, that's it. Okay, so it's a very nice summary here. And then last time I didn't have the right slide, so I found my slides. And okay, so we're going to talk about capacitors. Okay, not too much into details, but I have to skim through. Now, for capacitance, you remember, use your equation sheet here. And remember last time there was a student found a mistake here. The voltage, you need to have a square root here. They are missing the square root. Okay, so equation sheet now. Look, that's going to be the unit about capacitance, so capacitors, and that will be the equation that you will need. Okay, so the capacitance, that will be the definition. So we're going to talk about it, but you have all the equations here. This one, we already know this one. Remember, if you have a capacitor like this, right? I'm charging the capacitor. I'm going to have an electric field. You have two parallel plates. Okay, I can disconnect. So that capacitor, think of it as a defibrillator. Okay, so let's do that in a nutshell. Okay, so it's not charged. So you connect your defibrillator to a high power supply, 100 volt, 200 volt, depending if you wake up someone dead or you want the heart to have a good pace. So anyway, you connect that to a power supply, then you are using this energy of the power supply, so electrical, like chemical potential energy if it's a battery, or electrical energy. That energy here is going to be transferred to the capacitor, and the energy will be stored inside the electric field. So an electric field is a way to store energy. Okay, we're going to talk about a density, energy density, how much energy per unit volume. So anyway, the power supply is doing work on the capacitor. So there is a transfer of energy. So first you are charging the capacitor here. Okay, so it's going to hold charges, right? You can disconnect it, and you see all the work that the power supply has done during the charge. It's going to be stored into the electric field. So this is called a parallel plate capacitor, and you're going to have energy stored. That energy will be proportional to the electric field square. It's uniform. You see the lines are equally spaced, and then it can hold the energy there, and then you can burp out that energy into a load. So for example, here that will be the capacitance. I'm going to talk about the capacitance, but the unit is in farad, so that will be picofarad. You're going to have some charges. Okay, so plus and minus the same charges here and there, and you're going to have some energy being stored inside the electric field, and then you can have a discharge. So all that energy is going to be burped out into the load, and you're going to have a flash in that case. You can slow the discharge if you have a large resistance here, or you can make it quick. So the idea of a capacitor, in that case, it can burp out the energy in a very small amount of time. It will burp out current. Okay, so it's a current burper. Very high current, very, very, very high, very short of time. Okay, so that's the idea of a capacitor. So if we go back to the equation sheet here, you see the electric field, remember, is sigma over epsilon 0. We have seen that. You can show that with Gauss law. Sigma is the charge density surface on per unit area, okay, which is the charge per unit area. And then the voltage, okay, across parallel plate capacitor will be equals to the electric field times the distance between the plates. Okay, we have seen that because the electric field is the slope. So it will be the voltage, delta V, over delta X or delta H. So you have this equation here. Okay, so that will be for a parallel plate capacitor. You have the energy stored in a capacitor. See, it's going to be also 1/2 the charge times the voltage. So you have the equation here. So the total amount of energy, so the total amount of work that the power supply has done, okay, putting energy into it. And you have the energy density, which is the amount of energy inside the electric field per unit volume. It depends on the electric field square. Okay, and we're going to talk about dielectrics, and we're going to talk about capacitance. So capacitance, it's going to be the amount of charge, okay, you can store per unit volt. So it's like capacity. Capacity is like a volume. So if you have a large beaker, you can hold a lot of water. If you have a small beaker, it's going to be a small amount of water. So same thing here. Capacitor is like a reservoir for charges. Okay, large capacitance means a lot of capacity. So large charge per unit voltage that you had applied. Okay, we're going to see that in more details. Just in a nutshell, the unit is the farad, and it's named after Michael Faraday. Okay, so that's the farad. And then you can, that's all the equations that you need. So for the next pop quiz, remember to know how to use your equation sheet. Okay, so let's go back to capacitors. Best example will be a defibrillator. So you're gonna charge, yes.
Second test, check potential.
I have two of you. No, I think it's a potential and circuit, what we are gonna do now. Okay, circuit, which is very easy. And circuit and potential, I think.
After capacitors.
Yeah, also. But the easy. We are not going to do charge and discharge. So I think, but I will get back to you. There is a practice test already posted, right? So after the spring break, but don't erase your memory. Don't erase your USB. Don't erase your physics USB during over the spring break. That will be nice. So anyway, you charge your defibrillator and then you're going to discharge it, for example, across the heart, and you can control how long it will take to burp out that energy. So you can burp in a very small amount of time, so that will be a spike, or you can burp over a very long time. Okay? You can control the time. You are burping out current, and that energy that transfer to the heart. The heart is an electrical system, so it's like a load, and it will start. It will start again. But this is called a parallel plate capacitors. But anything that can hold charges, you can find how much charge it can hold per unit voltage. So if you have a Van Graaff generator, okay, that's a capacitor because you can hold charges, not much, like nanocoulombs, for the voltage applied to it. Okay, so this is a capacitor. It's called a spherical capacitor. It's not very efficient because that's not many charges that you can hold, but that's good because it cannot kill. Okay, so this is plus. That means somewhere you have minus, whereas the minus should be in the ground. Okay. So that will be the definition for a capacitor. You have two conductors. One is plus, the other one is minus. In between them, you're going to have the electric field where the energy is being stored. That will be the equation for the density, energy density, so energy per unit volume. You can find the total amount of energy. So you connect that to a voltage, work is done, and you are storing energy into the electric field. Okay. Again, this is a conductor, so there is no electric field inside, and there is no charges inside. Okay, so it was a big breakthrough in the 1930s for when I'm scared to say his name. I'm not sure if I'm say it right. So this guy was from MIT in the 1930s, and he's very famous because he came up with the high-speed camera, right, using a capacitor, okay, that will burp out the energy in the plasma lamp. So you will have a flash, very bright flash during a very small amount of time, so you could do pictures, photographies like this. Okay, it's called a stroboscope, right? I don't know if I have. So that's one application of the capacitor. So that was in the 1930s. Okay, so you have very high intensity flash over a very small amount of time because the capacitor discharge in a small amount of time. So if you buy the disposable camera, okay, you have those flashes, the same idea, stroboscope, and that's what you get, right? Flash, 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 flash. It's very cool because you can see the free fall. Okay, so lots of application. For example, we can say this is also like a capacitor. So you have positive charges here, let's say, because of friction. Of course, all the negative charges are going to come there. So negative and positive, two conductors here. and you have a very strong electric field between, then you have a breakdown. So a capacitor can break down. If the electric field is too large, then you can have a breakdown, you have a discharge. So this is the old system for a spark plug. They don't do it this way. So nowadays they use two coils, I think, but at the time they will charge a capacitor. The capacitor, okay, will hold the charge, discharge in a coil. So very high current during a small amount of time. The current will change very quickly. So then you have high voltage during a small amount of time, and that will make a spark. Okay, that's ignition system, but the old system. So you have a lot of application. You can use that as in RAM, random memory, because you can have the capacitor charge or not charge. So charge 1, not charge 0, 110011110. You can hold information. Okay, so for example, here, I don't know where it comes from in my previous life. I was playing with electronics, but you see here, any PCB will have like those capacitors. You see these little cylinders? So you have big one, which means they have high capacity, so they can hold more charges for the same voltage, and you have small one here, and you can have even smaller one than this. So any of those things here will have capacitors. Okay, so you can use capacitor to store energy. So here's an example. San Francisco, they have this train, and when the train breaks, instead of losing that energy is going to be stored in a capacitor, and then it will go back. Okay, so you can use a capacitor to store energy for a little time. You can use it also as a timing machine, because a capacitor can charge, discharge, and you control the time it takes to charge and discharge and charge and discharge. So you can use that for a microcontroller, for example, which is a tiny computer, right? You need some timer. It's you can control the frequency here. So 16 megahertz microcontroller, you're going to use capacitors as a timing machine. The clock, that's what it's called, a clock. So you can use it as a clock. And then you use capacitor to filter noise. Okay, so if you have high frequency noise and you don't want that noise, you're going to dump that noise here into the capacitor, and you have a good signal. So in a microcontroller, you also use a capacitor with the power supply to get rid of the high frequency noise. So you use a capacitor as a filter. You can use it as a high frequency filter or low frequency filter. So it has many applications. Okay. Also in biology, the human body, that's gravity. Okay. Human body is electrical in nature. So when you have a action potential, when you have a signal going through the nervous system, you're going to have polarization, depolarization, polarization, depolarization, and so forth, and so on, and so forth, and so on. You can see that as a capacitor as well. Okay, it's holding energy. Okay, capacitor can be deadly, it can kill. So you have to be very careful. They are very fun to play with. Okay, but they are very deadly. You have to be very careful with them, because it's the charge. It's not so much the voltage. So you can have a small voltage with a lot of charges, and those charges, right, they flow as a current. And the idea of a capacitor, you can do a very high spike in current, and you can kill. So you have to be very careful when you are working with capacitors in any device, you don't know if the capacitor is charged or discharged. So you need to take a screwdriver, for example, to make sure it's discharged and it doesn't discharge through you. Okay, so this is someone very famous in the electronic stuff. It's very funny. And you can see that capacitors can be deadly. I- So these are giant capacitors. So this is called a Jacob ladder, right? And so anyway, I have to be very, very careful. He's just lucky. I think he's very lucky. And there is a very nice video. It's called Fun with Ultra Capacitors. So I'm not going to show you the video because it takes time, but if you're in electronics, I recommend it because he explained how it works. And it's a very nice channel. If you like electronics, it's super interesting. So this is called ultra capacitor. So even though the voltage, you see, don't have to be very high, it has a huge capacity, huge one. So it means it can hold a lot of charges, and so it can kill. So I'm not going to show you, but you find the video on YouTube.
You're shorting the cap plus 5 cent coin.
I don't think it's legal, right? You're not supposed.
To make these PCB traces light up like glow wire. Finally, let's make some random sparks again, just for the hell of it. The called equivalent series for 2 volts of out-80s.
Oh, he did something worse, you know.
Turns out the insulation on that wire.
He put them in parallel
Let's try it like 10 cents.
or in series. I think they are in parallel because in parallel you add up the charge. So it's yeah, they are in parallel. Mm. So it's you can find it on YouTube. It's also interesting. I don't know this one. What is that? No, it's another demo, but it shows that when you have a non-conducting material, you can force charges inside. You can have charges inside the non-conducting conducting material. And that's a student of mine. He built the capacitor, so you can build the capacitor. So anyway, that's for the fun. Okay, so relationship. So this is a parallel plate capacitor. So the charge that you're gonna be able to hold, okay, is the capacitance times the voltage. Or it's better to remember that the capacitance is a property of a capacitor So each capacitor has a capacitance. It's going to be how much charge you can hold per unit volt. Okay, so usually a capacitance can be very small. So for example, 4 picofarad. Okay, so you can find the charge. So the math is easy. So for example, capacitance. So that will be in coulomb. This is in farad, and this is in volt. So if you have a 4 picofarad, that means the capacitance is 4 times 10 to the negative 12. Okay, the voltage that you are using to charge a capacitor is 9. So you can, this is a 9. So you can find how much charge you can hold. Okay, so the charge is just kidding. I was kidding. So the charge here, the equation will be the capacitance, which is 4 times 10 to the negative 12 times 9. So the charge is 36 picocoulombs. Okay, so it's a very simple equation. Agree? Yes, so this is capacitance. So it's a property of each capacitor. I don't know if I have pictures of capacitors somewhere here. So for example, this one has 4700 microfarad. So it's like a blueprint. Okay, just tell you how much charge it can hold. And the 35 volt means you should not go over 35 volt, because otherwise, believe me, it's popping in your face. And it's not very cool because it's full of acidic stuff. So it pop, right? So that, and those capacitors here are polarized. So you have to be careful. One side only to the negative sign of the power supply. The other side will be positive. And then you have, these one are more expensive, so it's very small. And you have the ceramic one. So these one are called electrolyte, but you have the capacity written on them. Okay, so it's like a blueprint. Okay, so we talked about that at the beginning of the semester. The ancestor is the Leyden jar, right? That's how they started to do the experiment. Name after Leyden, because no one can say his name. So unless you are Dutch, Muschenbroek, something like this. So instead they call that after the town he was from. Okay, and he found out if you have capacitors in parallel, you increase the amount of charges that you can store. Okay, so that's you can make a capacitor if you want to do a demo. Here inside you have water. You can have a nail that will be aluminum foil. So you always have two conductors. In between, you need an insulator. Okay, so you can hold energy inside the electric field. Okay, so this is called a parallel plate capacitor. But of course, we need to find a way to increase the area, because if you increase the area of the capacitor, you're going to increase the charges. So you increase the capacity. So let me show you a demo. So if I go back to the demo here, okay, if I increase the area, it makes sense. But you cannot do that. Of course, you buy one capacitor on another capacitor. But if you get another capacitor with more area, it makes sense that you have more space to hold the charges. But there is so much charges you can hold because they don't like each other. Okay, they repel each other. So when you are charging a capacitor, first it's easy to put the first charge and the second charge, and then it gets harder and harder and harder, and there is so much you can put. It depends on the capacitance. So the capacitance depends on the area. Okay, you can decrease the area. So if you decrease the area, you're going to hold less charges, right? Decrease the area. I have an issue with my mouse. Okay, you see the charges that you can hold, it's going to decrease. So it makes sense that for a parallel plate capacitor, the capacitance is proportional to the area. So if you multiply the area by 10, the capacitance will be multiplied by 10. If you multiply the area by 2, the capacitance will be multiplied by 2. So this is true for a parallel plate capacitor. That's the capacitor you are using in electronics. Now, if you decrease the distance between the plates, it's like you're increasing the motivation. Okay, they see that they are very close, right? The minus are very close to the plus. They say, oh, it's almost there. So you can put more charges in that case. Now, if you increase the distance, you put less charges because they say, oh, it's not even worth it to try, right? They're not motivated anymore. So the capacitance is inversely proportional to the distance between the plates. Inversely proportional to the distance, but proportional to the area. As you increase the capacitance, you increase the charges, you're going to increase the electric field. You see those electric field lines, they get more packed as you, so less packed, more packed, less packed, more packed. Okay? Decrease the distance, you're going to increase the electric field. Make sense? So the equation for the capacitance is very simple. For a parallel plate, parallel plate, parallel plate, parallel plate, parallel plate. Do you have the equation for a parallel plate? It's going to be, it's not there. It's not there. Yes, it's there. Okay, it's there. So for a parallel plate capacitor, the capacitance is proportional to the area, inversely proportional to the distance between the plates, and you have epsilon 0 here, which is 8.85 times 10 to the negative 12. Okay, again, the definition, that's only for a parallel plate capacitor, but sometimes you have a spherical capacitor. So in that case, you have to do the calculus. In that case, you use that equation. Capacitance is the amount of charge that you can store per unit voltage. Is that clear? Okay. And of course, you never see like a capacitor with two plates parallel to each other. It won't fit on a PCB. So what you do, you roll them up. Okay. And in between the electrodes, between the conductors, you need to have some insulator. So you have the two electrodes, in between you have insulator. So it could be air, which we don't use in electronics. Usually they have some kind of dielectrics, which is an insulator. So to have a capacitor, you need two conductors. One is positive, the other one is negative. In between them, you have an electric field. In between them, you have an insulator, because if you don't have an insulator, you have a breakdown. Okay, and you can boost the capacity depending on the dielectrics or insulator that you can have. Okay, so that will be the equation. You have, in that case, capacitance is the area over the distance. You can boost the capacity by placing some, not air, but some kind of insulator, special kind of insulator, and they call that dielectric. So back then it was paper. They would use paper. Now they use mica, or they use other stuff. So it's going to boost the capacitance by a factor K, the dielectric constant. Okay, we're going to see that, but it's just to show you the here. You see, if now you have a capacitor and you use some kind of insulator between the plates instead of using air, like paper, you're going to boost the capacitance by a factor K, which is called the dielectric constant. Okay, so I can show you that here. Let's see. So I have a capacitor here. I'm going to charge my capacitor. Okay, I have some charges here. I have my electric field. I have my capacitance. Capacitance will be the charge per unit volt. I have the store energy. Okay, the voltmeter I don't need. It will be whatever voltage that is. Agree? Now, if instead of air, which we don't use in electronics, of course, that will take, you don't shove like two plates inside a PCB. So you roll. But to roll, you need some kind of insulator between the plates, which is used to be paper. So I'm going to shove it into here. And you see, it's going to increase the capacitance. Because you always have some kind of dielectric. You can see the amount of charges that you can store for the same voltage is going to increase. So it increases the capacity. So it's called a dielectric. Because it's, why does it increase? Because inside here it's going to be polarized. Okay, so here it's going to be minus, that's going to be plus. So you have more plus motivated to come here because you have a minus there. So interestingly, we're going to see it's going to decrease the electric field. But in that case, it's going to increase the capacitance. This is, if you want to understand capacitor, sometimes it's not intuitive. So this is a very, very nice simulation. Okay. So which one will result in increasing the capacitance? What can you do to increase the capacitance? B, very good, right? You decrease the distance, you increase the motivation, because of course plus wants to go with minus, and you increase the area, you increase the volume. Okay, so if you have access to the old capacitors, you can open them, and then you see it's like a roll. It's like rolling, and you have paper as an insulator. Maybe you can still do that today. You watch the video. I forgot about this video. I don't know, but you find some people that will. But the electron, I don't know if you want to open that because it's juicy inside. But that's the idea. Okay. So rolling means you increase the area, you increase the capacitance. So these are types of capacitors that we use today. Of course, on PCB now they are able to print them up, right? They don't use those cylinders except in the one I show you. But you have variable capacitors, you have all kinds of capacitor. Is that clear? And you have to be careful to read here the maximum voltage. If you go over that, it pop. It's a polarized capacitor. If you don't plug it the right way, it can also get upset. So it's very sensitive. It has a feeling. Get upset. There's many things you can do with capacitors. If you put them in parallel, you can make a coil gun. So it means you're going to store energy into those capacitors. The energy will be burped out in a very small amount of time with a very high current. So you can have a coil, which is an inductor that will, so you transfer the energy to the inductor. The inductor is like an electromagnetic, an electromagnet, and you can shoot something, a projectile. The military people, they have this. So if you are interested in making one, you can look it up. How to make a coil gun. It's fun. Have to be careful. See, coil gun. if you want to make one. So you have a coil and you have a capacitor. So you go energy store in a capacitor to energy store in a coil. Coil can be used as an electromagnet, so it can shoot a projectile. Okay, so that was, sometimes you can buy those. So you can buy those, and instead of put it in the trash after, you can you can get the capacitor here. Okay, you can get back the capacitor. It's a very high capacity capacitor, 3300 microfarad. Okay. Any question? Yes, you. Okay, but you can have so these are for plate capacitors, right? But you can have different shapes. So you can have a parallel plate capacitor. So that will be the equation. Okay. This equation here will be true for any capacitor. Anything that will hold charges, okay, the capacitance will be the charge per unit volt. Now, the equation to find the capacitance depends on the geometry. So this is the best one because you can hold it, increase the area, and you can hold a lot of charges. So that's the one we use in electronics. But sometimes you need to find also how much charges will be stored if you have what it's called a spherical capacitor. So for example, the Earth is a spherical capacitor. It's going to hold charges. So you can do the computation. If you have a Van Graaff generator, so that will be the plus, that will be the Van Graaff generator. That here will be the ground. Okay, so that will be the plus, that will be the minus, and that can be very far, that will be the ground. So you can find the spherical, the capacitance of a spherical capacitor. And for that you have to do calculus. Okay, so I refer you to textbook. It's nice computations, but it's all math, and you have to use that equation here. Okay, how much charge per unit voltage, and the voltage you have to find it using the electric field. And how do we find the electric field using the voltage? You have to you have to derive. Okay, so there is some calculus behind it. You have also a cylindrical capacitor, and that will be the equation here. Okay, so you can look to your textbook to see the computations, but you see why an application in environmental science, the Earth is like a spherical capacitor. Okay, because here you have the ionosphere. And so you kind of have charges. Let's say you have positive charges here and you have negative charges there. So you have an electric field in between, and you can have a discharge happening if the electric field is larger than 3 million Newton per Coulomb. But it's a capacitor, it's holding charges, right? And you can find how much charges it can hold. So you can place that here very far away and find how much charges you can hold. So anyway, that will be the equation. And you have a textbook here, 20.13, and the computation is in your textbook. Is that clear? So I think there is always like, if you want a Van Graaff generator, for example, don't space out, stay. Okay, so let's say you have a Van Graaff generator, right? So the radius is A. Okay, so you connect to a power supply, it's going to charge, and you have plus, 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 plus. And you remember what the electric field looks like, right? It's going to be radial like this, but somewhere you have minus, right? Where is the minus? It's very far away. You have some minus, but it will be in the ground. So in that case, the B, so this is B, that's where the minus are. It's going to be very, 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 very far away. It will be the ground. It will be the ceiling. It will be the ground. So in that case, that distance will be very, very, very big relative to the size, that distance B. Okay? So can you find the capacitance when B is so big? So that's going to be, so that means that C equals 4 pi epsilon 0 B. So which one is big? B is big. So that goes away. Okay. 1 over very big. 1 over infinity is 0. So at the denominator, you're going to have something like this, right? So when you divide, you multiply by the reciprocal. So it's going to be epsilon 0 times A over 1. So that will be the capacitance of a Van Graaff generator, because the minus is very, very, very far away. So you can simplify, you can take the limit. So that will be the capacitance of an isolated sphere. Okay? So capacitance is just going to tell you how much charges you can hold for a given voltage applied to the two conductors or applied to the device. So it's not that hard to understand. It's a headache to do the calculus. It's a headache to find that. You have to do calculus, but you can do it in your textbook. Okay, and then a lot of application with the cylindrical capacitor. Okay, same thing. Inside it's going to be positive here. Outside it's going to be negative. In between you have an electric field. And why is it important? Because when you have signal, this is called what it's called? It's called the cable, coaxial cable. Okay, so coaxial cable, that will be your signal here. That will be your dielectric, and that will be your positive charge. And then after a while, you're going to have negative charge here and positive charge over there. So when you are doing electronics, you need to find how much charges it's going to build up. Okay, and you can do the computation and you use the equation. So that will be a cylindrical capacitor. Is that clear? So we need to know those computations to know exactly how messed up our signal will be. Because if you have a signal and you have this capacitance building up, it's going to slow it down. Okay, so you have to do those computations. And you have the computation here. So that will be a cylindrical capacitor, that's a parallel plate capacitor, that's a spherical capacitor, and that's an isolated sphere. The unit is the farad. Okay? It's in a nutshell. So the first capacitor ever built was done by Michael Faraday. Didn't go to college, hardly have an education, went to school until he was 12 in England. That's was not very nice. England was not very nice if he didn't have any money, but he taught himself science and he was very good at the experiment, and he built the first spherical capacitor. So again, you have two conductors. In between, you have some dielectric, so insulator. So you're going to boost the capacity at holding charges. Okay? Are you with me? So I don't know if you remember that, but we discussed that. So if you have two plates, right, two conductors, charged positively, charged negatively, the electric field goes from the plus to minus. If you have a dielectrics in between, this dielectrics here, it's an insulator. So the electrons, they cannot move freely. Okay, you cannot have electrons moving all to here and the plus left behind. But the molecule gets polarized. Okay, it's called polarization. So you're going to have minus, minus, minus on one side, plus, plus, plus on this side. So now inside here, you have another electric field because it goes from plus to minus inside, and it will make the total electric field weaker. But still, it will boost the capacity. So it's a story with the fish. I don't know if you remember the fish, but I don't know why is the fish. Yeah, exactly. Here it is. Um, so you see, if you have an electric field, because this is plus, for example, and this is minus, and you have a dielectric here, so it's an insulator, it will make the electric field weaker. So that's how it knows no good to it. If you have a conductor, it will make the electric field stronger. So it knows, the brain knows that it's good to it. So if you have an insulator inside an electric field, it will make it weaker, but it will boost the capacity. We talk about that. That's a tangent. So we did? We did. Okay, okay. Did we talk about that? That's super cool, but I don't remember. It has to do with action potential. And the action potential is going to be electrical energy. That energy is going to be stored inside the configuration of proteins in the muscles. So that means that will be potential energy like a spring that's being compressed. And when the muscles want to contract, you have some calcium that will it will be like a switch, and the muscles will contract because this protein is releasing that energy store. So it's all about distribution of charges, electric field, and electrostatic energy. So you can Google it, how it works. Super interesting. You know, since 2018, we know that it's something very new. For those who are in biology, we know that the cells inside the body, they talk to each other. They send text message, like little package. Inside the text message package, you have RNA, you have protein. So if there is inflammation in the body, let's say there is a fatty liver, it will send those packages, those SMS, and it will say to the other cells, you know, oh, we are sick, we don't feel good, we have inflammation, get inflamed too. But if you do a lot of strength training, if you do a lot of bodybuilding, for example, it will do the opposite. So it means that those muscles, they make something called myokine. Have you heard of that? That it will make like some protein that will be inside those packages, and it will be sent over all of the body and say, oh, look, he's exercising, she's exercising. So we need to cool down the inflammation. We have to get better. Okay, so it's not about the look, it's really about health. And we only know that since 2018, those little SMS that will be sent by the muscles to all the body to decrease the inflammation. Isn't that amazing? And it takes you back to physics. Everything is physics. It's not biology, it's physics, right? So let's go back to our business. I don't know where we were now. Okay, Michael Faraday, dielectrics. Okay. So now if you have a dielectrics, so now if you have an insulator like paper, for example, in between, instead of having just air, you're going to boost the capacity. Even though the electric field will get weaker, you boost the capacity. Okay, so for example, dielectric constant, that will be the variable k, the number k. You see, if you have air, that will be 1. If you have paper, that used to be what they had in capacitors, you boost the capacitance by 3.7. So you multiply by a factor of 3.7. Mica, you multiply by 7. So this is more expensive. You can have water as well. But I don't know how it will work in an electronics to have water. And you have different material here, right? So let's do it quick. The computation here. So a keyboard, you have a key here, and when you press the key, you change the distance. By changing the distance between the plates, you increase the capacitance. And because you increase the capacitance, then it can hold more charges. And if it's holding more charges, that means you have a little current flowing. So it's like a signal. There is the key B has been pressed, so, put a B on the screen. Okay, so if you push, you decrease the distance, you can hold more charges, so more charges will flow to fill the reservoir, and it will send a signal. So you do the computations just for the sake of doing the computation. So the equation capacitance equals dielectric constant times epsilon 0 times the area divided by the distance between the plates. So we have the distance, okay, which is 5 times 10 to the negative 3. That will be the area, and that will be the dielectric constant. It's in your equation sheet, but make sure you have you have the right units, right? Because sometimes you have to be careful with the unit. This is in meters, this is in meter square, and this is in farad. And that thing here is 8.85 times 10 to negative 12. And that's just a constant. See, it has no unit. It's a constant. 3.5. Okay, so that will that that is what you should get. So the first one is going to be this one. Okay, that's good. And then you decrease the distance. You're going to increase the capacitance. So if you want to save some computation, you can just find the ratio between the distances, okay, and it's inversely proportional. Okay? And of course you want to open your book, blah blah blah, for the calculus, right? It's a good practice. I have a question. Yeah. For this, just find the difference in distance between the two, and then use that. No, you don't find the difference in distance, but what you can do just you compute this, and then you find the ratio between the distance, right? So you do 5 divided by 0.5. So you 5 divided by 0.5, 0.15, so 5 divided by 0.15, and whatever number you find, you can multiply this one. So you don't have to do it again. Okay? So dielectrics, you see what it does here. It gets polarized. Okay, we did that, blah, blah, blah. Okay, dielectric. Okay, we get it. Okay, we understand that. Okay, so energy stored in a capacitor. Okay, so you have the equation in your equation sheet. Yes.
Yeah, are they going to give us the dielectric?
Yes, yes.
Okay.
No, no memorizing. I cannot memorize it, so I cannot ask you to memorize. I'm very bad at memorizing. So, equation sheet here. Here, that will be the energy, U. Okay, so that's like potential energy. That will be the energy stored in the capacitor. And here you have the density, the energy density. So the energy per unit volume. So each time you have an electric field, so it could be an electromagnetic wave, it could be light. Light is made of an electric field that will induce a magnetic field, that will induce an electric field, that will induce a magnetic field. So you can find how much energy you have in the electric field. So each time you have an electric field, it doesn't have to be a capacitor. Then you can use that equation because any electric field is a storehouse for energy. So that will be the energy per unit volume. So each time you have an electric field in space, you can find the energy. You multiply by the volume if you have the energy density. So this is always true for any electric field you have. And this is only true for a parallel plate capacitor. Okay, so energy density, it's proportional to the electric field square. You can see how they did that equation. They found this equation just for the capacitor, parallel plate capacitor, but it will be true for any electric field. Okay. Okay, so the energy is capacitance times voltage square. So if you take a capacitor with the same capacitance, but for example, you multiply the voltage by 2, the energy will be multiplied by 4. So what do you think? Be very good, right? Very good. So it's proportional to the voltage square. But except that you have to be very careful because in any capacitor, it will tell you the maximum voltage. Maximum voltage. When it says 35 volt, maximum is 35 volt. If you go over that, it's gonna bang, it's gonna burst. So that will be the symbol for a capacitor. So it's like two plates here. Okay. You can have capacitors in series, and these are called capacitor in parallel. So when they are in parallel, okay, then you boost the amount of charges that you are storing. So in the video, that's what he did. He took ultra capacitor and placed them in parallel, so it makes things even worse. Okay, it's going to boost the amount of charges. So you can you can look at your textbook and they show you how to do the to show that the equations. But when capacitors are in parallel, you are increasing the capacity. That means you can store even more charges. So if you want to make a coil gun, you want capacitors to be in parallel, so you boost the charges, right? So if you don't find the capacitor that you need, you can take two capacitors in parallel and the capacitance will just be multiplied by 2. If they are in series, then you use that equation, but you don't have to worry about that. But you can see that here. I don't know, I'm lost here. So if they are in parallel, you're going to boost the capacity. Okay, so these are capacitors in parallel. No, are they in parallel here? No, they are in series. So if they are in series, you lower the capacity. So you can play here, but it's a parenthesis. I'm not going to go into that. But if they are in parallel, yes, you're going to increase the capacitance. Blah, blah, blah. So one thing I'm skipping, but it's interesting. It's called charging and discharging a capacitor. So we say you charge a capacitor through a resistance, or you're going to discharge the capacitor through a resistance. You can control how long does it take to discharge or charge. And you do that with a resistance. So you don't worry about that. That's for those who are going into electronics, for example. But there is something called the time constant, which is the resistance through which you are charging times the capacitance in second. So that time here is going to give you how long it takes to charge the capacitor to 67% to the maximum voltage. So this is called the time constant. But I'm just talking about the concept. You see, first it's very easy to charge it because you have a plus. Okay, plus is fine. And then another plus. Okay, two plus. Oh, they don't like each other, but they are fine. But as you put more pluses and more pluses and more pluses, they start to really, really, really hate each other. It's crowded over there. So it takes more work to reach the voltage, to charge a capacitor to your voltage. You can discharge a capacitor and you see it's an exponential decay. Okay, so first it's going to discharge very quickly and then it's going to discharge very slowly. So back then, when we had those cheap phones, like now the phones are good, but when you were charging a phone, it will be charging very quickly to 20%, 30%, and then it will take forever to get to 100%. Okay, and then it seems when the phone is discharging, you get to 5% like forever. You say, oh, I'm still 5%. I can text. Ah, I can't. So for those who are interested, I have a video here that you find in Dropbox, only for those who are interested, that show you how it's done. So you have a capacitor, you have a power supply, and you have a resistance. Okay, and the voltage, 120 volt, at the end, when no current will flow, the voltage across the capacitor will be 120 volt. But it will take time to charge it. So it looks like this. And I don't like myself, like my voice. Okay, so it's going to charge. Blah, blah, blah. Okay, so look here. I'm going to close the switch. Close the switch already. Closing the switch. Look, look, look. Look, 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 look. Very quickly. And then very slowly. Okay, and now the capacitor is charged. There is no more current. The voltage across here will be 120 volt, and I can discharge it in a load. So you're going to have a flash. Smaller the resistance, the time will be smaller. And then it takes forever to get rid of everything. Now, if I look at what it looks, I'm going to close the switch. Look, 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 look. It's charging, 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 charging. It's gonna get to 10 volt. And now it's charged. There is no more current. Okay. And then I'm gonna discharge it. Ready, ready. I'm gonna open it so I can hold the charge. I'm gonna discharge it. I'm gonna put my load. No, no load. I'm just connect those two. I'm gonna discharge it. And it should go exponential decay. I'm going to do it again. Blah, 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 blah. Discharge. So it's charged. I'm going to discharge it. Wait. Discharge exponential decay. Okay, so this video is in Dropbox if you're interested. So if you have access to capacitors, for example, you can do a cool demo if you know what you're doing. If you don't know what you're doing, don't do it. Because capacitors can kill, okay? So this is a capacitor just for demo, okay? And this is a USB cable that I split in two. When you connect to that, it's going to be 5 volt. So I'm going to have 5 volt. I'm going to connect that to the capacitor. So 5 volt here, 1 farad, but it's very resilient. Okay, it's not going to pop because it's for demo. So it says 5 volt, 1 farad. So 1 coulomb per volt. Okay, so that's my USB. From the USB, you should get 5 volt across. So then I'm charging my capacitor. 5 volt from the USB, I'm charging it. And it's polarized, I have to be careful. You can find that it's going to increase to 5 volts. So you are charging your capacitor. 5 volt. Okay, it doesn't take long because I didn't put any resistance. So it's going to hold the charge. I'm going to disconnect. Okay, disconnect, not touching it. If you touch, that's it. It's going to discharge. And then I take a load. Blah, blah, blah. I don't know what I'm talking about so much. Okay, this is my load. I have to be careful. Boom. Very intense flash. Very bright. And then it takes forever to discharge. So first it's going to discharge using an exponential. So first the current will be very high and then it's going to decrease, but it takes forever. So you are discharging your capacitor. So that's why it can be deadly, right? If you put your, in that case, of course, but a capacitor can be deadly if it's discharging inside you. And you see it takes forever to fade away. So capacitors, very fun. Okay, so charging, discharging, done. Any questions? So that's an easy unit. We're going to talk about circuit, and I will show you my way to do it. But you can use the book way to do it to solve circuits. So in any circuit, it will be like a hydraulic system. So hydraulic system, you have a pump, right? So it's energy. That pump here will increase. It's going to do work on water. Okay, it's going to increase the potential energy of water, and that potential energy will turn into kinetic energy. So if you want to increase the potential energy, it depends on what? on the, if you want to increase the potential energy, you increase the, so in that case, in the hydraulic system, so imagine you take a gallon of water, place it at a height. Okay, you have potential energy, and that potential energy is going to be delivered here. High, the height, right? And remember, voltage is like height. So likewise, in a circuit, you have a power supply, you have voltage. The voltage will be the potential energy per unit coulomb. If you increase the voltage, you're going to increase the pressure, right? You're going to go higher up. So you increase the potential energy. That potential energy is going to turn into kinetic energy. So you have the power supply, so you have the voltage. The voltage is like the height. 9 volt means 9 joule per coulomb. Each coulomb of charge has an energy of 9 joule. And those coulombs of charge will deliver the energy to the load. Okay, so then they come back here, the coulombs of charge, little charges here, they come back here, they have no more energy, and they get a boost again. So it works, it's very similar. Now, how can you increase also the energy? You have the height, but you also have, like if you close the valve, or if you open the valve, what's going to happen to the, it's going to spin faster, right? If you open the valve, you increase the amount of water, you increase the amount of energy available, so it's going to spin faster, agree? So likewise, to deliver energy to the load, you have two ways to do it. You can increase the voltage, but you can also increase the amount of charges being produced by the power supply. Okay, so if you have, instead of having 3 coulombs per second, you have 4 coulombs per second, you have more energy available. So you can play on the voltage, which is like the height, and the amount of charges delivering the energy to the load. So you have the power supply and you have the load. So energy, chemical energy, and then electrical energy, and then light and heat. Okay. So right now, I'm gonna pretend that Franklin Roosevelt was right, and it's not electrons flowing, even though it's electron flowing, but let's say it's coulombs. So I have my power supply. I'm gonna take my load here. Load. Okay, I'm gonna measure the current. I can measure the voltage, and I'm gonna close the circuit. So you can imagine here that this little arrow, each one of them is 1 coulomb of charge. So each coulomb of charge, okay, has an energy of 9 joule. Now, if I increase the voltage here, I don't know what's happening. It's not cooperating anymore. It's stuck. If I increase the voltage, what's going to happen? I increase the pressure, so it's going to flow faster. So energy will be delivered faster. I'm increasing the power. I don't know, it's my mouse that's not cooperating. So let's do that again. Okay, so what you are measuring here is the current. So you see, so this, each one of them is 1 coulomb of charge. If I increase the voltage, it's like increasing the pressure, so the charges are going to flow faster. So number of charges flowing through here will increase. So that means here I have 5.80 amps. That will mean 5.80 coulombs. Those little things here, arrows, will flow per second. So I can count 5.8 coulombs per second. If I decrease the voltage, right, it's like decreasing the pressure or decreasing the height, it's going to move slower. So energy will be delivered, but not at the same rate. Okay, so I can increase the rate at which energy is delivered by changing the current. So that will be the voltage. Voltage is the energy per unit charge. And the current, you can think of that, how fast the coulombs are flowing. Is that clear? And you see it has a resistance here, 10 ohms. So we'll talk about that next time. But that's the idea. Okay, so this is called the load, this is called the power supply, and you need to connect everything together. So power supply has a EMF. Okay, so if you measure the voltage across a power supply, that's what we call the EMF. So we need some EMF. Okay, so you can get an EMF from a battery, from the outlet, from the power supply, from a voltaic cell, fuse cell, and all kind of devices here. Okay, so anyway, just to give you the idea, you have the power supply, you have the load. So the battery, okay, this is plus and the minus. The battery, through chemical reaction, is doing work on 1 coulomb of charge. So this is 1 coulomb of charge. So it's going to raise that energy to, this is 1.5 volt, right? So the energy of each coulomb of charge will be raised to 1.5 joule. And that energy, okay, will be delivered to the load. But then you can control how many of those coulombs will be produced per second. And that's what we call the current. So the current is the amount of coulombs per second, and the voltage is the energy per coulomb. And you do have an electric field, so the battery is doing work against the electric field. It's going to increase the voltage, the energy per charge, and that energy will be delivered to the load, and each coulomb of charge comes back, no energy, it's going to start again. Current is, we pretend that you have coulombs flowing, but in reality it's electrons flowing. Okay, so we'll do that. And that's going to be easy, super easy.